So for this construction, what I'm going to do is move over to Geometry Sketchpad. What we're given is, though, that the trapezoid, we have JK parallel to ML, and we want to construct the altitude from J to ML. What you have to understand is altitude is going to go from a vertex. Actually, it doesn't have to go from a vertex. What it's going to do is it's going to go perpendicular to one of the bases. Okay. Now, it asks us to go from vertex J. Okay. The key is, though, perpendicular to that base ML. All right, so we'll go over to Geometry Sketchpad because I can't simulate the compass tool on this particular setting. So I'll go over here. What I would personally do first is I would put the center of my compass tool on J. I would actually find the radius that hits M. You don't have to. All right, there are other ways to do this, but I would construct that circle. And what happens is I find another point right here that is the same distance from J as M is. So essentially, you're kind of creating an isosceles triangle here. Now, if you can find the perpendicular bisector of these 2 points, okay, what it'll do is it will pass through J and be perpendicular to ML. So move number 2 is I'm going to try to construct, and I'll just pick any radius. I'll pick a radius right about there, more than halfway. So what I'm going to do is I'm going to use this radius, and I'm going to construct a circle by center radius. Now, I've got to use the same radius, but I want to put the center of my compass tool over there. All right, now this point, this intersection down here to J should be the perpendicular bisector of these 2 points. What does that do? Well, we'll see in a minute here. We'll construct this line. Wherever that hits to J is our altitude. We're going to leave all the construction marks. What we'll do is we will label it, sure, B. All right, so JB, that's going to be our altitude. It's going to form a right angle there. So those are the construction marks. You don't have to actually make the full arcs. Okay, so now we'll talk about this. So remember, this point, let's call M, and maybe this is point P1. What happened was these 2 segments are the same, so this is an isosceles triangle. And what I constructed here was the perpendicular bisector of these 2 points, which gives us the perpendicular, and it hits J. Okay, so that's it. All right, determine its date in terms of pi, though. In terms of pi, the area of the sector intercepted by a 40-degree arc of the circle. Okay, with a radius of 4.5, 40-degree arc. So this angle is also 40 degrees. Central angles are equal to their intercepted arcs. What I usually do for area of a sector is I first get the area of the full circle, which is pi r squared. And I'm going to leave it in terms of pi because that's what they want us to stay in. So it's 4.5 squared. So the area, I believe, is going to be around 20. Let's go get that. Yeah, 20.25. So it's 20.25 pi is the full circle. Now what I would do over here is I would go 40 degrees out of 360 degrees, because that's the full circle, times 20.25 pi. So I calculated that, and you could call it 2.25 pi. What would that be? 9/4 pi is the equivalent whatever your calculator says. So what I do is in my calculator, I don't multiply by pi. I just multiply these numbers together. It comes out 2.25, and then we attach the pi to it. Okay. 27 is Cavalier's principle. So the shortcut is to use that. Okay. These two volumes are going to be the same because of it. And here's what we go with. Basically, Cavalier's principle is this. When the area of the base, the bases, and the heights of two prisms are equal. We could say 3D objects, but we're going to say prisms because these are prisms. Are equal, then the volumes are equal. Now, for this one, the base of figure A has a height of 5 and a length of 8, and it's a triangle. Okay, so this is the base, the area of the base of figure A. So we'll do figure A first. Figure A, you could actually go calculate them both, or you could just state Cavalier's principle. Figure A, area is going to equal base times height, and the volume. I apologize. Volume is base times height because it's a prism, but the volume, or I'm sorry, the base, the capital B, is the area of the base. Now, since it's a triangle, it's 1/2 times base times height. So it's 1/2 times 8 times 5, and that comes out to 20. Now that's for figure A. Now the height is, of course, 14. Now what we're looking at is figure B. Again, the volume is base times height because it's a prism, even though it's tilted, called oblique. The B, again, 1/2 times base times height. Now this time, the base is 5, the height's 8, but still in the area of 20. Okay, so both figures have a base area of 20 and a height of 14. So their volumes must be equal. Don't actually have to figure out what those are, but I think what 280. Don't have to figure out what they are, you just have to know they're going to be equal. Okay. When volleyballs are purchased, they are not fully inflated. Okay, a partially inflated volleyball can be modeled by a sphere whose volume, okay, 180 cubic inches. After being fully inflated, its volume is 294 cubic inches. Oh boy. Yeah, let's just go with, we've got to work this one backwards, assuming it is a sphere. I think it is. We're going to use the same formula, but we're going to come up with different radii. So it's 4/3 pi r cubed. So we're going to solve for r. We're going to have to replace v with their respective volumes. Sorry, replace v So we're running two separate problems at the same time. Okay, so now we'll do the math here. I'm probably going to combine 4/3 and pi and then divide both sides by that. So I'll come back in a minute. Okay, so just did some calculator work here. What I first did was multiplied 4/3 times pi to get 4.18. Now I want to divide both sides by 4.1888 number. Divide both sides, you get 42.97 on the left, and those eliminate so that r cubed on the right. Now this is where it gets a little bit tricky here. This is the new step. You haven't experienced this a whole lot before. Okay, so what I want to show you is to get rid of r to the third power. The third power is what we want to get rid of. You have to cube root both sides. So the inverse of third power is third root. So now r comes out of there. I lost that number for a second here. Let me just get that back. 3.5. So basically 3.5026. That's not the final answer. I better not circle that. That is just the radius when it was not fully inflated. Same process over here. So pretty similar process here. Okay, I multiplied that out, same number. We're going to take the third root of that number and get that 4.1249. Okay, so now we're going to subtract. Change in radius is going to be 4.1249 minus 3.5026. So it's looking like 0.622, nearest tenth of an inch. So the change in the radius is 0.6 inches. Okay. In right triangle ABC shown below, altitude, so it's already a right triangle. Okay. Altitude CD, that means that's a right angle. Explain why they're similar. Now, it doesn't mean you have to do a full proof, but that could be an option. You just want ABC and ACD. You just want these. Okay. So here's what I'm going to start with. First point is angle ACB. Now this is not a full-on proof, it just says explain, so I don't have to be quite as many steps. So angle ACB and angle ADC are right angles. Angle ACB is a right angle because triangle ABC is a right angle, or right triangle, with hypotenuse AB, right? So the right angle is across from the hypotenuse, so that's that reason. And angle ADC is a right angle because an altitude makes a right angle with the side it touches. Okay. All right, got to keep going though. That's just, probably didn't need all that, but I was just verifying why those are right angles because I said they were. Now, angle A, if you look right here, both of those triangles have angle A is one of their angles. Okay? I could have made another step here. I probably could have said angle ACB is congruent to angle ADC, and that's because all right angles are congruent. And my last statement would be they're similar. ABC is similar to triangle ACD by angle-angle triangle similarity postulate. Okay. All right. AB is congruent to DE. AC is congruent to DF and angle A. Okay, so they are congruent. All right. Triangles are congruent. By side angle side. So we know triangle ABC is congruent to triangle, gotta go right over DEF. Okay, so there must be a sequence of rigid motion transformations that will map one onto the other. I think this is a 4-pointer. Let me check that for a second. No, it is only a 2-pointer, so that influences us. We don't have to quite say as much here. All right, so we know that they're congruent by side angle side. There has to be a sequence of rigid motion transformations that will map one onto the other. What I like to look for first is orientation. Okay, so if you look at A to B to C, that orientation is counterclockwise. Now, its corresponding is DEF, right? And DEF, if we move, it is same direction, counterclockwise. Now, what I would do in this situation is not use no line reflections or an even number, whichever one you want to do. So I'm going to go no line reflections because orientation. Triangle ABC and triangle DEF are the same. So I want to preserve that. No, I don't want to mess that up. So let's just use a translation, then a rotation. So first is going to be, my first move is going to be, I'm going to translate triangle ABC by the directed segment. Some of you might use vector. That's good. There's nothing wrong with that. It's just in this course we talk about directed segments. So let's try to use the terms in this course. And what that would do is go, I'm just going to say C to F, right? CF. Okay, that maps point C onto point F. All right, so we're going to do that. And then just estimate. So there's C prime. Let's move the same direction, same amount. Let's assume that's B prime. There's A prime, right? It's really good to just sketch that. I know it's not great, it's not perfect, but if you sketch that, it's going to give you a lot of credibility. Now, we're going to take, rotate triangle A prime, B prime, C prime, centered at point F by an angle. Now this is going to be tricky. You can probably get away with that maps A prime to D. Technically, I should probably say angle A prime FD. You know, if you want to explain it. Okay, that's it. All right, last one of the 2 pointers, part 2s. Line N is represented by the equation 3x plus 4y equals 20. Determine and state the equation of line P after dilation. Okay. Now, first thing I would do is get it in slope-intercept form. So these are some mechanics that hopefully you were taught. So I'll just show those. And that's the current line. Okay, so this is the original or pre-image. All right, so let's graph that. So I graphed the y-intercept of 5. I went down 3, right 4 from there. Or up 3, left 4. So this is the, I wish I had a straight edge, but this is the original line. This is line N. The original, okay? Now, the point we're going to dilate through is centered at 4, 2. Okay, that makes it interesting. All right, so the center of dilation's on the line. Okay, so here's what I would say. The point 4, 2 is a point that is on line N. A dilation of a line centered at a point on the line gives us an image that is the same line. So the equation for line, what is this? P is the same equation, 3x plus 4y equals 20. That's it. All right, so there's the work and there is the explanation. That'll be it for this video, and the next one will get you the part 3s and maybe even the 4.